This video will cover a solution guide to problem 42 from chapter 13. Four identical masses of 8 kilograms each are placed at the corners of a square whose side length is 2 meters. What is the net gravitational force on one of the masses due to the other three? The only forces acting on these masses is the gravitational pull each mass is exerting on each other. Let's consider the mass at the bottom left corner. This mass will experience attractive forces from the green, blue, and orange mass, which we can calculate using Newton's law of gravitation. Because the green and orange masses are exerting forces completely in the x or y direction, their contribution to the net force is quite obvious. The green mass will only contribute to the y-directional force felt by the bottom left mass, and the orange will only contribute to the x-directional force. The blue mass, however, is diagonal from the mass of interest and will have both x and y components of force contribution. If we call the direction the force will pull the mass we are considering r hat, we can calculate the magnitude by using the same gravitation law we used for the green and orange masses. Because the masses are arranged in a square, the diagonal line splitting the square in half forms 45-degree angles. So in order to get the x and y components of the diagonal force, we simply rewrite the r unit vector as cosine of 45 degrees in the x direction and sine of 45 degrees in the y direction. If you're familiar with the unit circle, you may remember that these two values are the same and gives the square root of 2 over 2 for both the x and y directions. We now have the component form of all three forces acting on our mass in the bottom left-hand corner. The physics has been completed at this point, and now this is simply a vector addition problem. To get the net force acting on our mass, we simply need to sum up all the x components of the force and the y components of the force. Doing so reveals that the x and y components of the net force are the same, which is what we should have expected since this is a square with equal sides and all the masses are the same. Since the magnitude of the force from the green and orange masses are the same, we would expect the resultant force to point towards the center of the square, which also happens to be the direction of the force from the blue mass. Therefore, when we do the calculation of the net force, we should find that it points directly towards the center of the square, no matter what mass you choose to examine. If the masses of each sphere were not the same, or the square became a rectangle, the resultant force would most likely not point towards the center. The problem would like to know the magnitude of the net force, so we simply need to plug our expression for the x and y components of the force into our familiar equation for the magnitude of a vector. Doing so, we find that the magnitude is the square root of twice the x or y component of the net force, since the components are equal. Simplifying and plugging in the numerical value of g, we find that each mass experiences an attractive force of 2.04 times 10 to the minus 9 newtons directed towards the center of the square due to the other three masses.